Morning. So today we're going to talk about a little bit more about the differences between linear, exponential, and quadratic functions. So take a second, figure out the do now. Once you have your answer, come on back. Okay, welcome back. So they want us to figure out the missing values in the table. Now, the first one is pretty simple because it's just the area. So if the length is 20 and the width is 30, the area would be 600. And then, of course, if the rectangular yard is enclosed by 100 meters of fencing, if the length is 40, then the width has to be 10. And that gives us another area of 400. If we were to plot this point or plot these points, what would the graph look like? Quadratic, of course, because that's what we're talking about. So again, we're going to look and see whether a pattern is growing linearly, exponentially, or quadratically. So on page 14 of your book, take a minute, pause the video, see if you can figure out how each expression represents the number of small squares in the figure. Once you have your answers, come on back. Okay, welcome back. So looking at this figure, the side is 6 squares, the bottom is 8 squares, and then for this missing part, from here to here is 2, and then on the top is 3. So the first expression, A, 6 times 8 minus 2 times 3, would give us the total rectangle of 6 times 8 minus the ones that are missing, the 2 times 3. Expression B would be if we were to take this part, which is 4 squares, by the bottom, which is 8, and then add the 2 squares by the 5. So they just made 2 different rectangles with it and then added them together. Expression C, 8 plus 8 plus 8 plus 8 plus 5 plus 5. They're just adding all the rows together. And then lastly, expression D, 5 times 6 plus 3 times 4, is the 5 by 6, which is this rectangle, and then 3 by 4, which is that rectangle, and then adding them together. Okay, patterns of dots. Study the 2 patterns. How are the number of dots changing in each one? Well, looking at step 1, I see it that they're adding another 2 dots. So they're adding another column of 2 dots each step. And then on step 2, or pattern 2, I see that they're adding another row and column, the same number of dots as the step. So how would I find the number for step 5? Well, for step 4 would be 1 dot plus 4 columns of 2 dots. And then step 5, therefore, for this one would be, again, 1 dot and then 5 columns of 2 dots. So for pattern 2, step 4 would be 4 rows and 4 columns of 4 dots. And then step 5 would be 5 rows and 5 columns. I'm not making this very square, but that's the idea of it. And they would all be square for pattern 2. Okay, complete the table with the number of dots. So really quickly forming or plugging it in, we knew that pattern 1 was 1 dot, and then we add a column of 2 each time. So basically every step I'm adding 2 dots. Oh, that is not the pattern. So for our nth, what would our nth be? Going back to our pattern, this is, oh, okay, so step 1, step 2, step 3, that's basically my columns, right? And then I add one more to it. So for my nth row, I could say 2n plus 1. 2 dots per column plus the one more extra. And then pattern 2, we said it was rows by columns, whatever step number it is. So that means I'm just multiplying. 2 rows times 2 columns is 4. 3 rows times 3 columns is 9. 4 rows times 4 columns is 16, 25. Oh, I'm sorry, I did not notice that changed. So this is 11, this is 25, but this jumped to 10, which I did not notice. So that would be 21, and this would be 100. And then the last one for n in pattern 2, well, I'm just multiplying our numbers together. So that's n squared. Okay. Plot the dots. What do you notice? Well, hopefully you've already seen for pattern 1, it's linear. Because we are adding the same amount each time. We even said we're adding 2 each time. And then pattern 2, we have 0, 1, 4, 9, 16, 25, and then 36. Okay. So on pattern 2, the dots curve upward because it increases from step to step. Definitely not linear. Okay. Expressing a growth pattern. So page 16. Here's the number of small squares growing, or is the number of small squares growing linearly? So let's count. So in step 1, I have 3 squares. Step 2, I have 6. And step 3, I have 11. Well, I'm adding 3 and then adding 5. So no, it is not linearly. It's not going up at a constant rate. So completing the table, we already said step 1 has 3, step 2 has 6, step 3 has 11. Okay, let's try to find our pattern. So 3 to 6, I'm adding 3. 6 to 11, I'm adding 5. I'm adding an odd number. So 11, then 18, then 27. 10 would be 102. 12 would be 146. And our pattern would be n squared plus 2. Hey, is the number of small squares growing exponentially? No, because there's not a common factor. Okay. And that is it for section 2. We're going to move on to section 3 today. I can recognize quadratic functions in different ways. So kind of building on what we just talked about. Okay. Page 23 in your book. Figure A is a large square, figure B is a large square with a smaller square removed. Figure C is composed of 2 large squares with 1 smaller square added. Write an expression. So figure A, if the side length is 4, the area would be 4 times 4, which is 4 squared. If it's x, we just said it's just that number squared. If it's 4x, we have to do the whole thing squared. So 4x squared is actually 16x squared. And then the last one, x plus 3, is the quantity x plus 3 squared. Area B, well, I have the square in the middle that's taken out. So we could just do 4 squared and then minus the 1 square taken out. So x squared is the same thing. You just do the x instead of the 4. If it's 4x, well, we already have the area of the entire square, which is 16x squared, and then we still have to take out 1 square. And then lastly, x plus 3, same concept. I'm going to square this and then take out the 1 square. And then lastly, area of C, I have 2 of them. So if I have 2 squares with a length of 4, we would have 2 times 4 squared, and then we have to add this 1 extra box. Okay. Same thing with x, but it would just be 2x squared plus 1. Same thing with 4x. So if I do 4x times 2, that's 8, actually 8x squared. And then add in, nope, I missed a number. So it's 4x quantity squared, which is 16x squared, and then 16 times 2 gives me 32x squared. And then lastly, the quantity x plus 3 squared. Because I have 2 of them, I multiply by 2, and then I add 1. Okay. Expanding squares. Page 24 in your book. Go ahead, try these, figure out what's step 5 and what's step 18. Once you have your answers, come on back. Welcome back. So in step 5, I noticed that step 1 has 1 square in the middle. Step 2 is a 2 by 2 square. Step 3 is a 3 by 3 square, and then all of them have 4 squares added at the corner. So step 5 would be that's really step 5. Here, that's better. Would be a 5 by 5 square in the center, and then 4 squares added. And then lastly, step 18 would be an 18 by 18 square in the center. That's really 18. Again, with the 4 squares added in the corners. How many small squares in each of these steps? Well, we said the center was the step number squared plus 4. So we could just figure that out. So for step 5, 5 squared is 25 plus 4 is 29. And then for step 18, if I just simplify what I said, we could do 18 squared and then add 4. And then by simplifying it, makes it a little bit easier to do number 2. Write an equation to represent the step number n and the number squares y. So y would equal, we said we have to square the step. So if we square the step, it's just n squared, and then add 4. So my equation would be n squared plus 4. And then 3, if we sketch the first 3 steps of a pattern that can be represented by the equation y equals n squared minus 1. Well, I know that n squared is just a square with that number of rows and columns. And then if we take away 1, well, we just take away 1. So if I do, write it in this corner. Step 1, step 2, and then step 3. Step 1, I wouldn't have anything because we would only have a 1 by 1, and then we have to subtract it, so we wouldn't have anything. And for step 2, if I do a 2 by 2 and then take away 1, we'd end up with that, whatever corner that you want to get rid of. So you could draw it like this also. On step 3, we have a 3 by 3 with, again, 1 corner removed. And again, it doesn't matter which corner you take out. Pretend those are even. Okay. So growing steps. The next step in the pattern, well, we're going, if I look at my pattern, we have 1 by 3, 2 by 4, 3 by 5. So therefore, step 4 would be a 4 by 6. And then it goes from there. Kieran says that the pattern is growing linearly because as the step number goes up by 1, the number of rows and the number of columns also increase by 1. Well, if we're talking about the columns and rows, yes, those are linearly because they're going up by 1 each time. 1 by 3, 2 by 4, 3 by 5. So 1, 2, 3, 4, 3, 4, 5. And then as we said, step 4 would be a 4 by 6. But if we look at the area of these, 1 by 3 is 3, 2 times 4 is 8, 3 times 5 is 15, 4 times 6 is 24. That is not linearly. So it depends on what part of the pattern you're talking about. If you're talking about just the rows or the number of rows, those are linearly. But if you're talking about the area, it is not linear. To represent the number of squares after n steps, Diego and Jada wrote different equations. Diego wrote the equation f of n equals n times n plus 2, and then Jada's equation is f of n equals n squared plus 2n. Are they correct? Well, yes, they are correct because if I distribute this statement, I get this statement. So they are both correct. Right? That is it for this lesson. If you have any questions, please ask. From here, go on your class kick and try the problems. Have a great day.